In this presentation, I'll be focusing and emphasizing upon the idea of implementing sonification as a sound object and the effective use of spatial parameter mapping in the context of astronomical data. My name is Michael Quinton. I've just finished my PhD, which was about the application of sonification with exosolar planetary data. I'm a musician and songwriter, and also come from a background in sound design for theatre, film, and sound installations. In this study, we investigated the design and evaluation of sonifications of accretion disks situated in various exosolar systems. The study was conducted with an astronomer who volunteered to participate and will be referred to as AD, a male in his 40s who has been an astronomer for some time. AD was interested in using sonification in his work to see if it could help him to classify characteristics of accretion disks and to reach a deeper understanding of the temporal spatial qualities of an accretion disk in relation to the parent star. The dataset consisted of light curves collected over an observation period of about 80 days. So here we see that there is an aspect of time in relation to movement as the accretion disk occults the parent star of a particular exosolar system. AD was interested in studying the fluctuations in light of the observed star. These fluctuations are called dippers and are caused by objects that pass between the Earth and the star. Dippers are usually caused by huge dust clouds that envelope the parent star and supposedly rotate in sync with the star's orbit upon its own axis or barycenter. It could also be possible that dips are caused by asteroids or planets. The concept of hearing an accretion disk is quite abstract unless the sonification in some way sounds like a whirling disk of sound grains. This description was given by AD when asked to describe how he could imagine the sound of an accretion disk. He describes it as an object with dimensions. Here we can point to the idea of replicating the accretion disk as a sound object. The idea is similar to the use of sound in theatre or film, where you have a sound that represents an event or object that are not necessarily on screen, but the audience immediately understands the event or object just by hearing the sound. Sound perception is based on impressions of dimensions of space, volume, significance, proportion, material, and time. In order to construct a sound object, then the sound designer needs to make use of the various psychoacoustic properties working in relation to each other to convey the proportions, qualities, and temporal spatial behavior which is being conveyed in the data. Rather than simply using one or two parameter mappings for sonification, multiple mappings are used to sculpt sound and give it a more realistic and tangible quality. We can see how all the psychoacoustic properties indicated in the slide all work in relation to each other, and that is why they must be mapped accordingly. If we imagine the accretion disk as a circular ring moving around the parent star, then this would point towards the use of surround sound to replicate the spatial movement of the disk. To form the shape and size of the dips, pitch, timbre, and amplitude are combined. These three aspects work together to convey impressions of size, magnitude, and movement, since the changes in spectral qualities of the sound convey distance and proximity. The sound design aims to create something similar to a sandstorm, but with enhanced pitch to make it easier for the user to hear distinctions. The spatial perception must also authentically replicate how the accretion disk is captured from Earth, where it is seen at a distance and flat representation with the clouds passing in front of the star. So in this instance, stereo sound representation is used. The model is based upon AD's descriptions. The designer must pay attention to keywords used by the astronomer during the interviews and evaluations. Grounded theory was used to be able to work upon a foundation constructed from the data gathered from the user. Descriptions of movement, time, size, material, and other characteristics equivalent to accretion disks give indications of how multiple parameter mappings can be attributed to convey these characteristics sonically. In this slide, we are going to hear examples of 6 accretion disks that were sonified. We'll be hearing the playback in stereo and at a playback speed of 1 millisecond. Larger dips were mapped to higher pitch rather than lower pitch. This was due to the fact that during one of the iterations it was found that when using lower pitch to represent the larger dips, the distinction of the peaks was barely audible, and it was hard to hear the difference between the dips. AD found that the sonification could easily be associated with the data. By association, AD referred to the familiarity of the soundscape. He could immediately associate to it and follow how the data worked within these parameters. This familiarization aroused strong mental images of what AD was hearing. AD described the sonification as being able to convey quantities such as size, hearing the different sizes of the dippers quite clearly due to the changes in psychoacoustic properties. He could tell whether an accretion disk consisted of many or few dust clouds and was able to get a sense of time in relation to how long they blocked out the light at the parent star. The sonification could clearly indicate whether there was a sense of regularity in a star system's accretion disk, which could possibly indicate the system is starting to cool down, allowing planets to form. A more haphazard system could be the sign of an exosolar system still in its infancy and of a more chaotic nature. The level of regularity helped with the classification process, where more regular systems could be compared to each other. This aided pattern recognition and brought out any unusual behavior that could indicate novel findings. The sonification was informative enough to allow AD to make rudimentary classifications given the limited time that was allocated for this task. Patterns immediately started to arise, but the findings would have to be double-checked at a later stage. Characteristics of the sound design show that the mappings were able to convey the data as objects consisting of dimensions of size, speed, and motion quite accurately. The sonification also helped to present a temporal spatial aspect that was not immediately perceivable when using visual methods. It provided information about the proximity of an accretion disk to the parent star. The faster the speed of the disk, the closer it is to the parent star, and vice versa. This temporal aspect of the data became more apparent through the sonification. Spatial mapping played an important role in the sonification design. Without it, certain characteristics such as proximity, aspects of the dimensionality of the sound object, and particular pattern recognition and classification would probably not have been as effective. In this study, spatial parameter mapping seemed to be an effective mapping for astronomical data due to its temporal or spectral nature. It seems to be the gluing element that solidifies the relationship between all the other psychoacoustic mappings in conjunction to each other. The conclusions that can be drawn from this study are that the use of familiarity in the sound design helped AD to make strong associations between the data and the sonification. Spatial mapping was important at conveying the aspects of time, dimension, spatial orientation, and association. Sound object replication enhanced the user's ability to recognize the size of dips and get a rough impression of quantities. By combining all the multiple mappings together to create the sound object, AD was able to use the sonification as a replacement of the 2D visualizations and numerical data.
Excellent. Thank you very much for a very interesting presentation, Michael. We already have a couple of questions in the Q&A window. Did AD talk about how long he would be able to sit and listen to this data versus how long he looks at the visualizations? From experience as a scientist, one has to sit for very long periods of time looking at the data. Did you consider ear fatigue in this sonification?
Actually, we did. One thing we did during the testing, before the actual testing started, was I gave him an hour or two to literally play around with sonifications, load them, listen to them, experiment with the interface that we built to manipulate the sound of the sonification. And one comment I did ask towards the end when I was asking about the fatigue and the aesthetics and the sound design, he said, well, I listened to it for all that time. I've been listening to the sonification throughout the day. I'm not tired of it. So even though it sounds quite harsh and quite brittle, but he found that the unpleasantness of it was more realistic to him. The grainy kind of sound was something he really related to the sand grains that he could picture as the dust clouds that were blocking out the light of this parent star. So on that level, we found it quite effective. Again, he has a background in sound, so he used to work in live sound engineering, so probably his tolerance for noise is a bit more than the average person who doesn't work in sound. But again, because we only tested with one person, we'd have to see whether or not the aesthetics would be agreeable to other astronomers who come from different backgrounds and probably different expectations as well.
I think there is a question on that end. Did you plan to conduct experiments with multiple scientists? Do you plan at some point?
Yeah, that's the future work that there was a slide for that. I had to take it out because it ran out of time. But yeah, that's one thing we'd really like to do. I mean, I designed another 2 sonifications based on different data related to exosolar astronomy, where we use similar techniques. So in total, we had 3 astronomers testing each and every one of them. And but it's too small a sample, even though each and every sonification was, accepted and people could understand the data, so on and so forth. But we do need a larger sample of astronomers to test it with.
And another question that's very interesting, when they first evaluated the sonic representation, did you have to explain the auditory dimensions, or was it intuitive and you didn't have to explain to the AD?
That's a very good question, actually. I mean, since the design was based on an iterative process, basically the astronomer was familiar with the mappings throughout the design process. So what we were doing was, well, I did the first requirements gathering interview, got to learn about the data, what it was all about, what the parameters were, started to try and get hints from him of how he could actually imagine this being represented sonically. We had long discussions about that. And it's surprising, they do give codes when they're talking. And we use grounded theory as a method of actually analyzing what was being said during these interviews and then building the model based on all that. So all the mappings kind of came out naturally. So when you're talking about temporal aspects and spatial aspects in astronomy, that's usually going to come through unless it's spectral data. And so we knew that was an important emphasis that was needed. And we knew as well that the spatial and temporal elements would be related to size and as well movement. So you've got the accretion disk literally rotating around the star every time the clouds coming in front of the star, blocking out the light. And some of maybe if you heard the examples, you could tell that some of the peaks were actually larger than others. Now that could mean that a dust cloud like that has actually lasted days rather than just hours or minutes. They're huge clouds. And so he had an idea, but the thing is, it was the actual testing then where he could test out these parameters properly So he had heard iterations of the sonification. The final one was obviously the one that was tweaked, you know, before he actually had a chance to listen to it. We tested then, and then he could say, right, all right, so I'm you know, getting a better impression of the sizes here, dimensions, temporal aspects, so on and so forth. And then the whole evaluation was based on scrutinizing this in detail. So it wasn't kind of, we had set questions, but it was open-ended at the same time. So if he gave a particular answer, we could dig in further and say, right, tell us a bit more about that. Why do you think, he kept saying that the model was quantifiable. Now, it's not entirely true because you can't really tell, you know, the time of day just from hearing to it, but what exactly do you mean by quantifiable? So he was giving him, he said, I can easily tell where you've got these dust clouds which do last longer, which last days or not. One other thing was one amazing thing actually that came out, which was very interesting, was that the speed of the disk spinning around the star varied. Now, this is something that graphically you can see it, but you kind of take for granted, and he probably didn't notice that beforehand. But when he was actually hearing that some of the disks moved slower than others and others faster, what that apparently meant was that the disks that were rotating at a faster speed were closer to the parent star. So you got the same thing in a solar system where you have planets. In our solar system, we have planets that are closer to the sun, which rotate at a much faster speed than the ones that are further out. And you've got the same phenomenon replicated throughout different solar systems, whether they're developed or not. And these are developing solar systems, so they're younger as far as we know. And these speeds were very interesting to him because he could also tell the sun's rotation around its own axis from that speed. So you can tell whether a star is actually turning at a faster speed because the accretion disk moves literally it's locked in sync with the rotation of the star and rotates at around that speed. But then according to distance, varies accordingly. And there are, you know, planetary ratios and so on and so forth, where astronomers can calculate these differences and harmonic relationships between bodies within the system.